Hi, I'm Caesar. In this video, I would like to talk about the Dytran, or if you are fans of Nastran, you also can call it SOL 700 solver, which is the explicit dynamic solver from Nastran solver. And Dytran itself actually is just a solver. So if you buy or install Dytran, you can actually only have this user interface. And for Dytran itself, we can run the folder or the file from the BDF file, which you can create by using text editor or using pre and post processor such as Patran. So in this tutorial, I want to use the Patran to make our workflow much more easier. So Patran and Dytran are parts of Hexagon now. So they are easily compatible to each other from the editing and anything else. So let's just start it. Just open the Patran and we make a new database and save it in your computer. Let's say I want to save it here, Dytran. And in this video, I just want to simulate a very simple phone, which is not actually a phone, it's just like a silhouette of phone with certain material and certain thickness and no complexity at all, just to make this tutorial easy to understand the basic workflow. So I will save it here, the drop test phone. And maybe for the explanation, wait a minute. The explanation of the theories, material, and the others will not detailed here because it takes time. So maybe I will make another video to explain the detail about the theoretical background, because explicit dynamic solvers involves a lot of complicated stuff like material definition and some advanced computational setups. So first we must define the code to be MSC Dytran, and the model we can import from external source, or you can make geometry basically here. But yeah, in this modern era, I think we just the CAD modeler are just available everywhere with the cheap price. So yeah, we just import. So we can import the IGES file, which I already prepared here. You can request this model, but I believe that you can make this very simple model. Oh, one thing I forget to convert the units, so I must delete it first, because the default here is sometimes using inch, so I need to remove the conversion unit. So yeah, my model was built in the SI unit. Then I want to make the ground, so this drop test will involve two objects. First is the phone and the second is the ground itself. So I must make the ground, or you can import it from your CAD model if you have, but if you don't, it is easy to make it here by using this face creation XYZ 1 meter. I think it's too large because it's just like a very small phone, so I will make it like 0.2 or about 20 centimeter. And the units used here are consistent. It means that you are using meter, and the other will follows like Pascal, Newton, and etc. Then to translate it in the center of our model, I will make the origin 0.1. So yeah, here we go. The center is here, but I want to make this simulation more complicated or more exciting by rotate it like a 30 degree maybe or 20 degree by using this transform, and I want to use the rotate, let's say 30 degree, and the coordination is 0.3, means that it is rotated in the z direction. If we want to rotate in the x direction, the coordinate will be 0.1. And yeah, I also want to delete the original solids, so just click here, and here we go. We can check it is okay, then we just click yes. And I want to give some little distance here, which can be done by using transformation. So I want to translate it in the z direction with the value of maybe 0.05. In this case, I don't want to make a real high input. Let's say if we want to draw test from 1 meter and we just release it with the 0 initial velocity, instead we can make it as close as possible to the ground, but with the input of initial velocity, which can be calculated easily by using the free fall motion from physics. I believe you know that equation. And we can make the object as close as possible to make the total time needed not that long, so we will save a lot of computational resource. Okay, just delete the original resource and click here in the solid. Let's check. Yeah, seems right. Or you can delete the auto execute and then apply. It's up to you. And yeah, here we go. We are ready with our geometry. Next, we want to make the mesh. So for the ground, I will make it from the quad mesh, maybe 0.01. Let's say, doesn't have to be refined. Well, just ground, and we will make the ground a rigid body. Actually, for actual ground, the wave propagates in the material must be considered, but yeah, that's not significant. But unfortunately, if we want to make that pressure wave, it takes a significant amount of computational effort. So yeah, it's better to make it a rigid body. Then for the solid, I will use the tetrahedral mesh. Unfortunately, we cannot use the hex mesh here because the geometry is not simple. But if you want to make a much better meshing, you can use the MSC Apex software, or you can, like break it down to some, like sub models to make a better mesh. But yeah, for this simple tutorial, I think we don't have to do that. And I will use the Tet4 for simplicity again. Just click here and guess the value. I think I can make it smaller. Yeah. We know that smaller the mesh will make the simulation better in terms of the resolution of the detail, but it will also need more time, because from this explicit dynamic simulation we must consider the current Lewis number, which is the relationship between the mesh size to the delta time. So the smaller the mesh, we have to make the delta time smaller, which means the larger the computational effort. So that's the trade-off you must consider. I think that's all for the mesh. Then we move to the loads and boundary condition. First, I want to make the rigid body object for the floor or the ground, which we will fix in all the directions, both for translation and rotation. For the application region, you just need to click one point as a reference. So yeah, that's it for the rigid body, so you don't have to block everything. Actually, you can make another, like another boundary condition, like a planar rigid wall or maybe displacement, but the rigid body object is the most firm to be used here. Then I want to also make initial condition for the drop test using the initial velocity. Let's say init val, it's just for the name, and the value, let's say -10 in the z direction. So the input is like this, 3 inputs which are x, y, and z, and you can also input the rotational velocity if you need it. And the application region, you just click this solid, I think it is the surface, so yeah, that's right. Or you can use the finite element to drag everything here, but yeah, it's up to you. Sometimes it is debatable which region we should use for geometry. It is much simpler if you want to just replace geometry or make edit the mesh, but sometimes the algorithm is just not really well, like in terms of reading the codes. Sometimes using the finite element selection is better, but yeah, if you want to edit the mesh, the selection will also good. Okay, other thing we must consider is the contact between the phone and also the ground. So we'll make a contact here. It's the name contact, and for input we don't have to input anything because it's just like friction and anything like that. And for the application region, I will select the here I will use the primary secondary surface contact. And the primary will be the ground, and the secondary will be the solid. Yeah, I hope it's right. Okay, just good. You can click preview, but sometimes it takes time, so I just skip that preview. Yeah. Next step, we will input the material, which is quite interesting here in the Dytran because we have a rich selection of materials. Let's say we want to make the phone mat material, let's say. For the inputs, we have, like a very rich selection of materials, which is one of the advantage of using Dytran. And for this simple tutorial, I will just use this Elas+ DMAT. Elas+ DMAT. Of course, every material has its own theory that maybe we will discuss in another video. And here I use the Lagrangian solid. And one thing that you must understand in Dytran is it is used to solvers which are Lagrangian and also Eulerian, so you can easily coupled simulation between the structure and also fluid effortlessly without the computational fluid dynamics solver, let's say. So it is very robust solver to solve like explosion or maybe underwater explosion or maybe crash with involving airbags of flow, yeah, and kind of thing. And the failure model will be maximum plastic strain. Let's say we want to input it like 1000. Again, the units are consistent, so if you use meter, it will be like a kilogram per meter cube. And for the modulus of elasticity will be described in the coefficients. And the first coefficient will simply the modulus of elasticity. We will input like 2 gigapascal. Of course, it depends on your own case. And modulus, shear modulus, I will input to 4 gigapascals. Then the yield stress will be 60 megapascal. Again, it is just on some arbitrary numbers, so you can input based on your own case. But one thing you must consider is the density change will also make the delta time also change. So it will relate it to the sound travel, sound speed travel in the materials, and the sound speed itself are determined from the density and other parameters. Okay, just apply. And we want to make one more material called a rigid with the input as rigid metric. Here we go. We can input density or maybe the mass here, but it doesn't matter. It's just like a dummy number because it's just rigid actually, and no moving at all. Just apply. Then we define the properties for the Lagrangian solid here. Phone and phone material, and the application region will be the solid 3. And again, for the 2D properties, we will use this shell elements. So it will be ground with material rigid, and we must input also for the thickness, but again it is just like a dummy number because it will not affect anything because it is not moving. Just apply. And yeah, I think that's all for the setups. And maybe I want to make one more thing here, is to group. I want to make a new group which I will use to display the post-processing for the phone. It is not a mandatory thing to do, but yeah, it is just to make our post-processing better. Yeah, let's say phone group by, and the last step is to define the controls of the execution. First we must define the time steps. Here I want to use the end time, which is 5 to the power of -3, which is a very short event. For the end step we just input some arbitrary number because we don't use that as the reference. Make it as large as possible so it won't stop the calculation. And then we will start at 5 at the power of -7, which is very small. It is also calculated automatically from, if you run and get some error, you will have some initial number, like initial guess to make the simulation of error. This is basically calculated from the corner number. We can discuss it later. and the minimum is just to make sure that the simulation will not error before it exceeds this minimum time steps. So the time step itself will be automatically updated based on the iterations. Let's say for the very high impact, the time step will be smaller, but for free motion, the time step will not or even make it larger. Yes, that's all. And inertial loads, which is the gravity we must input here. Let's say 9.01 81 to the minus z direction, which is important if we want to include the potential energy of this object. And the last thing we must consider, actually we can run this simulation, but we will not have the result, unfortunately. So we must make the output request here. Let's say phone, and I want to make the output for the element output for time step, and we'll use 1 to the power of minus 4. So every 1 to the power of minus 4, it will be saved. So it will be like it will be every, so our simulation will be 5 to the power of 3, and we will save it every 1 to the power of 4. So we will have about 50 results, or 50 motion, or 50 step to make the animation or the data. So the smaller this number, the larger the number of animation, or the smoother the animation will be, but it will take longer and takes higher memories on your computer. And this number must be smaller than this small start time steps. And here we go. For the saving, maybe just take some arbitrary number. So larger is better, but if you have a very long simulation, you can divide the archive file into some separated files, which divided for its saving per file. So let's say if you make 50 files, if you save it like a 10, so you will have 5 folders, and so on. And next we want to define the location of the result in this phone group, which is group that we just made, just to make this selection easier. Actually you can use other selection like a tria or other elements, but yeah, using this group you can easily define the location, let's say if you have more than one paths. And the result will be Eulerian solids, Lagrangian I mean. Then I want to make the result maybe just for the stress, pressure, and strain. Of course you can explore anything here, but yeah, I just want to check these 3 results. Okay, and then we'll just apply. And actually if you click apply button, it just actually make the BDF or bulk data file and not run it into Dytran. So you must open the Dytran here manually and search for our DAT, which is here, DAT file. And if you have the license, you can make the parallelization by using this SMP. But yeah, if you don't have the license, maybe the number of parallelization will be limited. Oops. If it suddenly become 100%, sometimes it is because of error. We just click this error summary here. Oh, the element number 945. Let's check which one it means by the element 74. Set face. Let me pause this. Oh yeah, I think I understand the problem. Because of these 3D properties, we forget to define the region, so the warning is the undefined region. Yeah, just apply it once more, wait until the process done, and yeah, we simply go to the other file and back to this file to refresh the date file, and let's try again. And here we go. Oh, come on. Once more. The initial time step is too large. Yeah. Okay, we can change it to 4 to the minus of 7. Minus 7. Yeah. Let's change this to the... So you must follow this number. So it must be smaller than this. So it will be 4 to the minus of 7. But yeah, for this... for smaller mesh, it will be smaller or need a longer time to solve. 4 to the minus of, yeah. Okay, just make it as close as possible to the suggestion number, but don't make it exactly same, because it will be error immediately. And yeah, this is the function of this error message, so you can easily check the errors. Oops. Okay, let's refresh again. And yeah, finally, just wait. It takes a couple seconds because it is just very simple simulation. For actual job with complex geometry and complex mesh, sometimes it takes like hours or maybe days before you can get the results. So, and for Dytran, actually you can do the modeling for like a shell element or 1D element, so it is always a room for simplification to make the simulation faster. And the parallelization capabilities for Dytran is also really well for your complex model. And yeah, after it's done, we just click the archive file and select the here, add, apply, wait until it's done. Then here we go. For the result, we will get the results versus time. So it will be time at 0 and the time at end. To make the animation, we just click the Ctrl A to select all, then display let's say the PLS is plastic strain and PLTS is the plastic stress. So I will check the strain and select the deformation result, just click apply, and here we go, our result. Of course, you can still tweak the values for the time steps. Oops, it is, yeah, stop. Not as our expectation, but yeah, you get the point for this simulation. But I want to change first for this undeformed, so I just want to make it a little better for the presentation. But yeah, it's up to you. But maybe I want to revise the time steps by first delete the result so it won't doubled, and maybe I want to make the end time twice as this, let's say 1 to the power of 2, so it will be twice longer from our initial simulation. But I will pause it and show the result after it's done. And here we go. Let's check our result with twice time as previously. Yeah, here we go. We get our simulation, and we can check the displacement or maybe the stress, let's say. We can see the damage of this part. And yeah, it is quite a long tutorials. I hope you enjoyed this video, and please comment if you have any questions related to this tutorial, or maybe you have any other requests related to other course. And you can also find me on Udemy, or yeah, so you can also subscribe my other tutorials there related to computer aided engineering. Thank you for watching. Bye.